So we're very pleased to have here with us Professor Bernhard Hanke. He comes from the other continent across the Atlantic, far away for him. So I'm very happy that he managed to come, and he has worked heavily in boardism. He has used them very much to obtain nice invariants of manifold. So we're very happy that you came all the way from Augsburg. So he's a professor at the University of Augsburg, and the floor is yours. Thank you, Tocayo, for coming.
Okay, thank you, Bernardo, for introducing me. So I'm very glad to be here. I was happy to receive this invitation, and it's also a very nice opportunity to give this talk. It's a very beautiful place, and I hope at some point I will return here. Okay, so we heard talks about equivariant methods in topology, but also in geometry, in particular in complex and algebraic geometry. And in this talk, I will also span a bridge to differential geometry and metric geometry. And so kind of the starting point for my talk is homology, which is in some sense the essence of equivariant topology, because group homology can be interpreted as the Borel equivariant homology that we also heard about of a point. Okay, so this is the basic definition of group homology of an arbitrary, say, discrete group in this talk. And so we write down its integral group ring, write down the free resolution, as we call it, of the ZG module Z. So all these modules here are free ZG modules, and the condition is that this is an exact sequence. Okay, so nothing interesting happened at this stage, but it becomes more interesting when we take the tensor product of the sequence with, for example, the integers. We can also take other alien groups here, because this process doesn't preserve exactness, not an exact functor. And this means that after tensoring with Z, we get homology. And this is by definition the group identity of the group G. It's a purely algebraic definition using general and basic notions from homological algebra. And then we can write down examples. For example, when we take the group of integers to the R copies of Z, with generators x1 up to xr, then we can write down the group ring. So it has an explicit form here. And right, and then we can write down a free resolution, for example, Kosul resolution, and compute its homology. It's purely algebraic machinery who does this. And then what we get, of course, is in degree n, the group homology is just a free abelian group of rank R choose n. So that's the algebraic part. The blue thing refers to algebraic notions. And now it turns out that we also have a different point of view on group homology, namely, this turns out to be the nth homology of the R torus, which can be written as a free quotient of the group Z to the R acting freely on R-dimensional real vector space, R to the R, by just translation. And so there's a deeper reason why this is true. Namely, it is actually the case that you can take any free contractible GCW complex, take the quotient by the free action by G, and then compute its singular homology. Now it turns out that these two groups are actually equal, or canonically isomorphic. So this is because the cellular chain complex of EG can be interpreted as a free resolution of Z. And therefore, we have this equality here. So this gives a different perspective on group homology. Okay, so now we have these two ways to come to this group, H star G. And now we want to see what it is good for in a specific setting of this talk. Namely, when you take a closed orbital manifold, M, there is a canonical way to assign a group homology class in the nth group homology of the fundamental group of M in the following way. You write down the classifying map starting from M with values in B pi 1 of M. So this classifies the universal covering of M, on which pi 1 of M acts freely with quotient M. And you take this map, take the fundamental class of M, it's an oriented manifold, and apply the map in homology phi star to it. And this means you get a class in Hn pi 1 of M. So in some sense, this can be interpreted as a characteristic class, homological characteristic class of the manifold. This can be done very generally, and so it's an extremely general construction. And now we would like to study geometric properties of M, which only depend on this class in group homology. And in this way, we obtain a link between group homology and more geometric concepts. In particular, I will concentrate on these two topics in my talk, namely on a concept from large scale metric geometry. This has to do with enlargeability of manifolds. And then secondly, I will talk about Riemannian geometry, more specifically about Riemannian geometry of positive scalar curvature manifolds. Okay, so let's start with the notion of enlargeability. This is goes back to important paper by Gromov and Lawson within the study of scalar curvature geometry, but it has a purely differential, topological or metric interpretation. So we call a closed-oriented manifold M enlargeable if the following holds. Put any Riemannian metric G on this manifold and choose any epsilon as small as you wish. And then there exists an epsilon Lipschitz map, so epsilon contracting map, from the universal covering of M, M tilde is the universal cover, together with the induced metric on the universal cover, induced by the Riemannian metric on the universal covering, to the standard round N sphere, which has the following properties. The degree of this map is different from 0. Of course, we have to think a little bit what this actually means, because the universal covering space is usually non-compact. By this, I mean that outside of a compact subset of the universal covering, the map is actually constant. So this is this bright blue part here. And then we have a well-defined notion of mapping degree. So this is one condition. And the second is that, the map is epsilon Lipschitz. But this must be true for any metric G and for any epsilon as small as you wish. For example, you can take the 2 torus or n torus if you wish. This is the simplest example of such an enlargeable manifold. You take some metric on it and take a small epsilon. The universal covering of this is just Euclidean space. If we choose the flat metric, which we can do. And then inside Euclidean space, when epsilon is very small, this means you just have to shrink this Euclidean space by epsilon, multiply everything by epsilon. And then still it is possible to map a large region or to wrap it around the N sphere by this epsilon contracting map so that we get a map of non-zero degree. So in some sense, this enlargeability means that the manifold or the universal covering stretches in all directions as far as you wish, or you can scale the universal covering as you wish. So this is this notion here. And actually, it turns out that this notion is, or if this holds for one Riemannian metric on M, then it holds for every Riemannian metric. So this choice is really not so important. The more important choice is the one of epsilon. So this is because every two Riemannian metrics on a compact manifold are by Lipschitz equivalent. Okay, so this is this notion here. And so we have some sort of metric flavor in this notion, more specifically large scale metric flavor. And it turns out that every non-positively curved manifold, such as the N-torus with flat metric, enjoys this property. And this is because you can pass to the universal covering and apply the Cartan-Adama theorem, which tells you that the universal covering is basically Euclidean space. And then you can do apply the same construction, or you can draw the same picture as here. And now what is the connection to group homology of this notion? This is a result I proved with Thomas Schick in 2006. It says that if M is enlargeable, then this specific class that we defined before, recall, this is the homological fundamental class of the manifold mapped to the M homology of the fundamental group of M using the classifying map phi. And it turns out that if M is enlargeable, then this class is different from zero in rational group homology. So then in particular in integral group homology, but this is even true in rational group homology. So this is certainly not a torsion class. And we call such manifolds M, which have these property, this property here, rationally essential. This is just a definition or a word. So how do we prove such a theorem? So what does this notion have to do with group homology? And yeah, the proof is by one picture that I will explain to you. So that's the proof. Why is that the proof? Yeah, so okay, so we are interested in this property here. And I mean, there are many models for the classifying space of a fundamental group of a space, for example, of M, or the fundamental group of M. So what we can do is we just attach cells to M in order to kill all homotopic groups in degree 2 and higher. So this means we attach cells of dimension 3, 4, and so on inductively. And now what I have to prove is that it is not possible that the fundamental class of M is killed during this process in rational homology. So I apply or I use the specific model of the classifying space B pi 1 of M. I just take M itself and then I attach cells. And this is what this picture here indicates. And now the question is it possible that after attaching N plus 1 cells to it, the fundamental group becomes, the fundamental class becomes a boundary homologically so that it gets killed? And this picture indicates that this is not possible. Namely, if you attach an N plus 1 cell like this one or higher cells, then because the dimension of these cells is larger than 3, these cells lift to the universal covering of M, and you just get a bunch of cells attached to the universal covering. You get as many cells as the fundamental group pi 1 of M has elements. Okay, and now assume that some of these N plus 1 cells have as boundary the fundamental class of M. And this assumption leads to a contradiction. Why? Yeah, so the reason is that I can choose epsilon as small as I wish. This means that each of these cells is mapped to a tiny region of these of the sphere Sn under this epsilon contracting map. And so there is no chance that when you map these cells to the N sphere, that the boundaries of these cells somehow span the fundamental class of Sn. This is impossible. And therefore, this assumption leads to a contradiction. So it is not possible to kill the fundamental class of M by attaching cells of dimension n+1 in this way, because these lift to the universal covering and are mapped by f epsilon for very small epsilon to tiny cells here, which so that the boundary of none of these cells can actually span or can be equal or homologous to the fundamental class of Sn. So that's the proof of this implication. So now we have a connection between a large-scale metric property and group homology, in the sense that enlargeability leads to a non-triviality statement of this particular element in group homology. Okay, and now we can make this construction or this discussion, we can lift it to a more abstract level. Namely, we can abstractly define what we call the large group homology inside the actual group homology. And this is done in very much the same way as before. If Bg is a finite complex, then we just replace the manifold M on the previous slide by this finite complex Bg, and then you pass to the universal covering of Bg, which is Eg. And now the question is, okay, take some homology class in Bg, like here. And now the question is this class a large class or not? And the criterion is the following. There must be a epsilon contracting net for every epsilon, as small as you wish, from the universal covering space of Bg, which is Eg, to the sphere of dimension equal to the degree or the dimension of this class that we started with, such that when you take this class here, you lift it to a locally finite class on the universal covering by a transfer map and push it forward, this class, to the sphere of the same dimension as the class. And this must be a non-trivial element in the topology of the sphere. So this is exactly the same construction as before, just using this complex Bg instead of a manifold M. And we are not necessarily taking the fundamental class of M. So there is no fundamental class of Bg, but we can just perform the same construction, or we can write down the same definition using any homology class of Bg. So the criterion is you lift it to the universal covering space using the transfer map, and for every epsilon this class, we must find an epsilon contracting map from the universal covering space to the sphere of the same dimension as the class. But what does epsilon contracting mean here? Yeah, you can just write down a model of Bg using a simplicial complex. And when you have a simplicial complex, then you have a canonical path metric on this. For every simplex, I mean, you can think of some K simplex as a standard simplex in Euclidean space. This is a metric space with induced metric. And so any simplicial complex has a canonical path metric. So write down a simplicial model of Bg, and then we know what it means that a map of the universal covering space is epsilon contracting. And again, this definition is independent of what simplicial model we choose for Bg, as long as it is finite, because if you take another simplicial complex, the two metrics that you get are related in a bi-Lipschitz way. It's a little bit more complicated if Bg is an infinite complex, which also may happen, but then you can push this whole construction or discussion to this case also, namely, whenever you have a homology class in Bg, you restrict your definition to some finite subcomplex of Bg, which carries this class and already has the same fundamental group as Bg, namely equal to G. So this is no big deal here. And in this way, we define large group homology, which is it's a certain subset of H star. So for example, 0 is not contained in this subset. So it's not a subgroup, right? So it's something else. So it's in fact, the elements which do not lie in this subset, which we call small group homology. So this forms the subgroup of the group homology. Okay, so we define the subset of large classes. And now, together with Michael Brunbauer, I proved some years ago that the enlargeability property, so whether M is enlargeable or not, is exactly detected by this characteristic class of M. So by the image of the fundamental class of M under the classifying map. And the criterion is that this class must lie in the large group homology. Okay, so we already saw how this is done in one direction, namely from here to here. And the other direction uses certain functoriality of this construction here. Namely, if we know that this class is large, then you apply an induced map from the universal covering of M to the universal covering of B pi 1 of M. And from this, you have your required map to the sphere. And then you just compose these two maps. So there's a very convenient functoriality behind this construction here, which makes both directions here true statements. Okay, so we can detect enlargeability of manifolds by this class, must lie in the large group homology. And so let me discuss one particular example. On the first slide, we saw the free abelian group of rank R. And so let's calculate the large group homology of this group. And as model for BG, classifying space, we just take S1, the circle, to the R, so the R torus, whose universal covering space is R to the R. And okay, so there is one large class, namely, you just take the top or the fundamental class of the R torus. So this is a large class, we already saw on the previous slide. And so all the R group homology of the of Z to the R, except 0, is large. And okay, but there are also group homology classes in degrees below R. Why are they not large? Yeah, the problem is that, okay, so the universal covering space, or E of this group here, is Euclidean space of dimension R. And now if you have a homology class in degree below R and you lift it by the transfer map to the space, then it becomes 0, because in degrees below R, the locally finite homology of Euclidean space of order dimension R is 0, just by Poincare duality. So these classes cannot be large. Yeah, so we can also deal with other large-scale metric properties. For example, we could extend the previous definition by saying, okay, we do not always take the universal covering space, but we just ask, okay, there must be some covering of M plus the epsilon contracting map to the N sphere. And in particular, it was asked by Misha Gromov a couple of years ago if these two notions, if these two definitions are equivalent or not. Using this concept here, you see that they are actually not, because if we allow finite covering spaces in the definition of enlargeability, then it turns out that the large group homology of Z to the R with respect to this new notion of largeness also involves classes in degrees lower than R. And so we have a difference here, and in fact there are manifolds which are enlargeable in this more general setting, namely we allow arbitrary covering spaces of M, but which are not enlargeable in the sense that we can always take the universal covering of M. And this is a little counterintuitive, I have to say. And so, yeah, it took us a while to find the examples, but this kind of abstract machinery or this general definition here really helped us in this process. And yeah, by the way, so the fundamental group of these counterexamples or these specific examples which distinguish several notions of enlargeability. So these are based on the Hickman 4 groups, a group which is has the property that there are no proper subgroups of finite index. So this is used in this example. And then we use the functoriality of this construction here. And now the question arises, because group homology is a purely algebraic concept, as we saw on the first slide. Yeah, are there any, is there a way to write down an algebraic, purely algebraic description of large homology classes? And this question is completely unanswered, so I don't have any idea how to approach this. But I think it's interesting to ask this, because this is an algebraic construction here. Okay, so this is enlargeability of manifolds. Now let's talk about scalar curvature. This is the second topic I would like to address in my talk. And the quickest, fastest definition of scalar curvature of Riemannian manifolds uses asymptotic volume growth of small balls in your manifold. Let's take a Riemannian manifold, M with Riemannian metric G, and pick a point in your manifold P. Now you write down the volume of the epsilon ball around P with respect to the Riemannian metric G. And you compare this with the volume of a Euclidean ball of the same radius of around 0. So this comparison happens by just taking the quotient of these two volumes and writing down a Taylor expansion. The leading term is 1. This is obvious. And the next non-trivial term appears in front of the term of order 2 in epsilon. This defines the scalar curvature at the point P up to a normalization constant, minus 1/6 to the n plus 2. And here we have the three toy examples that we should keep in mind. Namely, in the spherical case, the volume of these balls is smaller than the Euclidean volume. And therefore, because we have a minus sign here, the scalar curvature at P is positive. Here in Euclidean space, it's 0, and this is hyperbolic space. Then scalar curvature becomes negative. Yeah, so scalar curvature is kind of the weakest curvature invariant, which measures, it's in terms of volume comparison. So this means in particular that, say that if the scalar curvature is positive, you cannot say so much about the geometry when you move in specific directions of your manifold. For example, if you take S2, this the two-sphere has a positive scalar curvature metric. Now, if you take an arbitrary Riemannian manifold and take the Cartesian product with your S2, then you can just shrink the S2, make it smaller and smaller, which increases its scalar curvature so that the scalar curvature of this product becomes positive. Here it's important to notice that if you take the product of two Riemannian manifolds, the scalar product, then the scalar curvature of this thing is the sum of the scalar curvatures. And so if you take S2 and you make it smaller and smaller, which increases its scalar curvature, then you can make the scalar curvature positive in any product with S2. And in particular, we see that if you have the product of two manifolds, one of which admits a positive scalar curvature metric, then the product also does. And so the product, in a very weak sense, looks like this example and not like this or this one. Yeah, so there's there are little more stricter curvature notions. For example, best known, of course, is sectional curvature and Ricci curvature. And so concerning the Ricci curvature, we have the Bonnet-Myers theorem, which tells you if you have a compact Riemannian manifold whose Ricci curvature is positive, then its fundamental group is finite. And or put another way, the universal covering is compact. And this maybe gives a better intuition about this roundedness, like here. So in the positive curvature world, things tend to be small. So it's kind of, this is the slogan, but in scalar curvature geometry, this is really not quite true, because we don't control so the deviation of geodesics in all directions. So there is a meta conjecture of Michel-Foromov that if you have a manifold which admits a positive scalar curvature metric, then at least in two directions, it must look like a sphere somehow. Or put another way, in at most n-2 directions, the manifold can be in the universal covering can be stretched infinitely. And so, for example, the n torus whose universal covering is the is Rn. So this is stretched in all directions, which then actually implies, and we can prove this, that the n torus does not admit a positive scalar curvature metric. So we have already a vague connection to large-scale geometric properties here, and this will now be summarized on this slide.
Can I ask you a quick question?
Yes.
About previous slide. Is it easy to say why there is no linear term there in epsilon?
Oh,
That's okay. It looks like there's no cubic term either.
that's true. There are just.
Right.
I'm afraid I'm not able to write down the Taylor expansion of the volume. But it's, yeah, there are just. Okay, so yeah, probably. I mean, there is an argument using symmetries of the Riemannian curvature tensor, but you need not write down the actual Taylor expansion. So there is a more systematic argument here, but I don't recall it right now. Okay, so so the meta conjecture says that PSC manifolds must be small in a certain sense. Of course, this has to be made specific because we already saw that S2 cross an arbitrary manifold, which can be large, can be largeable, admits a positive scalar curvature metric always. And here's the specific way how we can make this precise, namely a conjecture of Gromov says, if the fundamental class of M is mapped to a non-zero class in the nth group homology of pi1 of M, or put in other words, if M is rationally essential, then M does not admit a positive scalar curvature metric. So this conjecture is still open in general, but it is known to be true in specific situations. Namely, at first, one has to find obstructions against positive scalar curvature metrics. And one source of these constructions comes from spin geometry and the spectral geometry of the Dirac operator, which I will not explain in my talk. I just want to mention it. But for this approach, we always need that M is a spin manifold. So its second Stiefel-Whitney class must be 0. And in this situation, one can really set up a machinery. And for most pi1 of M, this conjecture is true. What does most mean? Yeah, this means all fundamental groups that satisfy the strong Novikov conjecture from non-commutative geometry can be used here. And for those, this conjecture is known to be true. But there is another obstruction, namely enlargeability. So if you have an enlargeable spin manifold, enlargeable as on the previous slide, for example, the n torus, then these manifolds do not admit positive scalar curvature metrics. I also would like to mention a cousin of scalar curvature, namely what people call macroscopic scalar curvature. Here one does not talk about the asymptotic volume growth for small epsilon, but one studies volumes of balls in the universal covering of a fixed scale. For example, volumes of balls of radius 1. And this macroscopic scalar curvature means that it is not possible to have a situation where you have a positive scalar where your manifold is rationally essential, and in the universal covering, the volume of all balls of radius 1 are extremely small. So at this fixed radius, this is what we are doing here. And it's quite interesting. I find this a very interesting development in metric geometry, that using this notion, this conjecture is true in general. So if we are working with macroscopic scalar curvature, then rationally essential manifolds are known not to admit these macroscopic scalar curvature metrics without any assumption on the fundamental group. And just to give you a sort of feeling what kind of arguments we are using in scalar curvature geometry. So in the dimension 2, there is an easy argument why the 2 torus doesn't admit a positive scalar curvature matrix. Namely, we write down the Gauss-Bonnet formula. calculating the Euler characteristic of T2. And it turns out that this is equal to the integral of the scalar curvature, which is equal to twice the sectional curvature or twice the Gauss curvature in dimension 2. And so if there was a metric G of positive scalar curvature, then here we would get a positive value, and this would contradict the fact that the Euler characteristic of T2 is equal to 0. And in some very vague sense, these arguments here, which use spin geometry and Dirac operators, are a generalization of this kind of argument. But it's, of course, there is much more I could say here. It's, so this is this kind of flavor of the arguments. Okay, so I just want to mention a connection between enlargeability and large-scale geometry concerning the universal covering space. Namely, if you have an enlargeable manifold, which is also spin, then we proved a couple of years ago that the universal covering of M does not admit any positive scalar curvature metric, which is quasi-isometric to a metric which is pi1 invariant, or in other terms, which is quasi-isometric to a metric coming from M. For example, if you take Euclidean space, say of dimension 3 or 4, then this does admit a positive scalar curvature metric. Namely, what you can do, you cut out a ball, say of radius 1 around the origin. The remaining manifold has the form Sn-1 times an infinite interval. On the Sn-1, you take the round metric and take the product with the infinite interval. And then you glue back this ball that you removed. So you have a cigar-like shape, and this has positive scalar curvature as long as n-1 is larger than or equal to 2. And but this theorem says that but if we require the metric on the universal covering space to be quasi-isometric to a pi1 invariant metric, then this is impossible. Quasi-isometric is a notion which is weaker than isometry. Isometry says, okay, the distance in source and target are exactly equal in metric spaces. And when you talk about quasi-isometric, quasi-isometries, then you allow scalings, and also it's allowed to add constants which remain constant, which doesn't vary over the space. So this is a weaker notion than isometry. Okay, so this thing here, so the C is quasi-isometric, this desert-like thing, because a large scale shape look equal when you are at a very large distance and you look at the space and they look equal. This is what quasi-isometry means. And here we use variant of Dirac operator methods, namely John Rawls' large scale or coarse index theory. And now I would like to come back to group homology. Before we studied large group homology and in connection with enlargeability. And now the motto is that positive scalar curvature leads to small manifolds. So it should also lead to small group homology. And therefore, we define the positive group homology of some group G in the following way. Take those group homology classes in degree n, which can be realized as images of fundamental classes of manifolds sigma n under some map to Bg. And sigma n is supposed to be a manifold admitting a positive scalar curvature. So this is the definition of positive group homology. And as you probably know, it's impossible to realize all group homology classes as Bordism classes, which this means here. And therefore, we allow manifolds with sparse Sullivan singularities. It's a more general notion than smooth manifolds. And at least away from 2, we can realize all group homology classes as Bordism classes using manifolds with sparse Sullivan singularities. So these are the positive group homology classes. And then we can prove a statement for non-spin manifolds, assuming that the fundamental group has odd order, in particular it's finite, then the property that M admits a positive scalar curvature metric is exactly measured, it's detected by this element phi of M that we considered before. Namely, the condition is that this element lies in the positive group homology. Please keep in mind that this positive group homology is sort of the opposite of the large homology that I discussed before. So these classes should be considered to be small. And for proving the statement here, we use the Bordism principle for positive scalar curvature metrics due to Gromov laws and Schön-Yau. So this connects differential topological constructions and the surgery with positive scalar curvature geometry, which is very important in the field. Okay, so we have this characterization, and now let's calculate a positive group homology in a particular example. Namely, I would like to compute the positive group homology for finite abelian P groups, where P is an odd prime. And it turns out that we can really compute the positive group homology, but apart from certain classes, which we call P toral, and the opposite are P atoral classes. So we call such a group homology class P atoral if the following holds. Whenever you take a bunch of one-dimensional cohomology classes in your group with coefficients in Z mod P to the L, and take their cup product, which is a cohomology class in degree n, and when you evaluate this on your given group homology class, then this must be 0. So in some sense, this group homology class is not the product of one-dimensional classes. This is what we call P atoral. And for example, if you take the group Z to the R and take any group homology class which is different from 0, then this is P toral for all P, because any such group homology class is detected by a cohomology class, which is the product of one-dimensional classes. And now this theorem, which I proved a couple of years ago, 2 years ago, is that if you have a non-spin manifold and pi1 is abelian of odd order, then if this characteristic class, this group homology class, which is associated to the fundamental class of M, this P atoral for all P which divide the order of the fundamental group, then M does admit a positive scalar curvature metric. This is true for fundamental groups which are abelian of odd order. And for proving the statement, we apply the theorem of the previous slide. And what we have to do is we have to compute the positive group homology for these fundamental groups here. Because if it turns out that, okay, all the group homology is positive, then this theorem here is a corollary, right? Because then, okay, in any case, phi of M lies in the positive part of the group homology. And now let's compute the positive group homology at first of one factor of Z mod P to the K. What is the group homology of these groups? Yeah, the reduced group homology with integral coefficients is equal to Z mod P to the K in odd degrees and 0 in even degrees. And in odd degrees, we can take as generators length spaces of dimension 2m-1 and take the classifying map to be Z mod P to the K and push forward the fundamental class of L 2m-1. And these elements generate the group homology in odd degrees, in odd dimensions. And now we see, okay, these length spaces here, they admit positive scalar curvature metrics as long as 2m-1 is larger than 1 in dimension 3, 5, and so on. So these are just portions of the sphere, and together with its round metric, the free Z mod P to the K action on this thing is isometric, and so the positive metric passes through the quotient, and so we have positive scalar curvature metrics on these length spaces. And so we see, okay, the positive group homology So this is the whole homology apart from the one in dimension 1, which is represented by a sphere S1, and S1 doesn't admit positive scalar curvature metrics. Okay, and here this is exactly the group homology part, which is R-total. Just the one-dimensional class would be a total class. And okay, in the induction step, we write our group G as the product of a group of lower rank with some cyclic group Z mod P to the K. We write down the König formula, König exact sequence computing the homology of the new group in terms of the homologies of the single factors. Here we have a tensor product, and here we have a torsion product, and these have to be studied separately. This is done in the following way. We see that alpha, so this corresponds to taking Cartesian products of manifolds or of group homology, of singular homology classes. And as we saw, if one of the factors admits a positive scalar curvature metric, then the product does. And for the torsion product, we have to be a little bit more careful. We use the fact that these elements here are represented by Toda brackets. And so we have to unravel the definition of Toda brackets using a geometric interpretation and then construct positive scalar curvature metrics on these manifolds, which come from these Toda brackets. And then the following is true. If you have two group homology classes here and here, and if one of them admits a positive scalar curvature metric, then the product does by shrinking the metric on one factor. And but here for the torsion product, both classes must admit positive scalar curvature metrics. And then the Toda bracket construction gives a positive scalar curvature metric on the class that is mapped to this torsion product. And so the especially difficult case are Toda brackets with classes of dimension 1, which do not admit positive scalar curvature metrics. And so what I prove is, if you have a PR-total class in your manifold, and we also assume that it's representable in the sense that the class is the fundamental class or can be represented by the fundamental class of a smooth manifold, then these classes are actually positive. And this is enough to prove the theorem from the previous slide. And the question if p-toral manifolds admit positive scalar curvature metrics is still open. So this is a conjecture, which I put down here. If we have a p-toral class for some odd prime p, group homology class, so can this be positive? Or put in different terms, we take, say, a manifold of dimension 5, for example, the 5 torus S1 to the 5, and then you can kill p times each generator of the fundamental group using surgery. This gives you a manifold with fundamental group Z mod P to the R or to the 5. And it is not known if such manifolds admit positive scalar curvature metrics or not. So this is still an open question. So we do not know whether these p-toral classes are large or small in the sense of positive scalar curvature geometry. But it's important here that we are really talking about finite fundamental groups, or this p is a finite prime. It's different from 0. We already saw that the actual torus, which we consider as a 0 toral manifold, does not admit a positive scalar curvature metric. And so this conjecture is true in low dimensions. It's open in general, but it's in low dimensions, it's true, assuming that the group G contains at most 3 factors of the group Z mod P, and the other factors are just copies of the integers. And then if the total rank of this the group here is at most 8, we can prove that such manifolds with this fundamental group, and if they are p-toral, then they do not admit positive scalar curvature metrics. This uses the classification of 3-dimensional PSC manifolds and the minimal hypersurface descent method. in scalar curvature geometry. So we have some partial results here, but in general, this question is open. In particular, if the fundamental group, or if the group G is just an elementary abelian P group without any Z factors. Okay, so we have an example of a four-dimensional non-spin manifold. It's easy to construct these examples such that the fundamental group of the first manifold is equal to Z mod 3 cos Z3, and the fundamental group of the second manifold is equal to Z mod 5 cross Z3. How do we construct these manifolds? You can just take the four torus and kill 3 times one generator of the fundamental group by surgery, and the same in the second manifold. And so then both manifolds are toral. The first one is 3 toral, working at the prime 3. The second one is 5 toral, working at the prime 5. And so using the previous slide, we see that these manifolds M and N do not admit positive scalar curvature metrics. So this shows that the corresponding group homology classes are not positive. This is what was written on the previous slide. But now something strange happens if we take the Cartesian product of these two manifolds and take the element phi. So remember that the image of the fundamental group, fundamental class of the manifold under the classifying map. This is the class in H8 of the group Z mod 15, Z mod 3 cross Z mod 5 cross Z mod 6. And this class is 0 by the König formula, because the tensor product of Z mod 5 and Z mod 3 is 0. This class is 0, so it is a positive class. And this means that the product of these two manifolds does admit a positive scalar curvature metric. This is quite interesting because we saw before when you have two manifolds, one of which admits a positive scalar curvature metric, then the product does. But the reverse implication is wrong, as it is shown by this example. So the product admits a positive scalar curvature metric, but the single factors do not. And so we have a slightly provocative statement here that when you take products of large group homology classes, so that should be even larger, but this is not true in this specific context, namely then the product becomes small, it becomes 0. So this means that, there are still many things to explore in this area, but I really think that that group homology is a good guiding principle and gives a very clear perspective on some geometric properties of interest to us in large scale geometry and in scalar curvature geometry. So I was relying on all the work of Brunbauer and myself from 2010, large and small group homology in the Journal of Topology. This example of the previous slide of these two single manifolds not admitting PSC metrics, but the product does. This is in a fairly recent preprint of Misha Gromov, torsion obstructions to positive scalar curvature, and the construction of positive scalar curvature metrics on manifolds with odd order abelian fundamental groups. This is in the paper Geometry and Topology from 2021. Yeah, that's all what I wanted to explain to you, and thank you for your patience.